Alright, in this video I want to give you some background information on the next generation science standards and specifically use a pre-teaching strategy to highlight some of the vocabulary that you'll use as you explore the next generation science standards. So the first term, or the first set of terms that we want to focus on, is the idea of science and engineering practices. So the framework document that was created by in this process identified three dimensions: science and engineering practices, cross-cutting concepts, and disciplinary core ideas. And those three dimensions need to be woven together into standards. So science and engineering practices are one of those three dimensions. They're called practices and not skills because they wanted to acknowledge the fact that it's more than just being able to do something. You need to have specific knowledge in order to engage in these practices. So it's more robust than a skill. There are 8 of these that stretch kindergarten through 12th grade. So within the standards, you'll see a progression of kindergarten through 12th grade in each of these practices. Some of these are very familiar, and we've seen them in different ways in different standards documents, previous standards documents. We have the first one is asking questions and defining problems. The second is developing and using models. The third is planning and carrying out investigations. The fourth practice is analyzing and interpreting data. Next is using mathematics and computational thinking, and then constructing explanations and designing solutions. The 7th is engaging in arguments from evidence, and the 8th is obtaining, evaluating, and communicating information, which this 8th one in particular, but also the engaging in argumentation, are very complementary to the Common Core English Language Arts standards for literacy in science and technical fields. What's important as you think about what these practices are is that these are the types of things that students should be doing and engaging in as they learn science. The second dimension outlined by the framework is cross-cutting concepts. So cross-cutting concepts are those ideas or foundational concepts that cut across all the different disciplines in science. So what they do, and what's really valuable about thinking and using cross-cutting concepts, is they provide an organizational structure for helping students understand the world. So it starts to build those connections between different disciplines of science, between physics and chemistry and life science and earth and space science and engineering. So with the 7 cross-cutting concepts outlined in the framework, again, will stretch kindergarten through 12th grade, and they include patterns, cause and effect, scale, proportion, and quantity, systems and system models, energy and matter in systems, structure and function, stability and change in systems. The third dimension outlined in the framework are disciplinary core ideas. So disciplinary core ideas, often abbreviated as DCIs, provide a small number of very foundational ideas or concepts in science. So what are these few ideas in science that stretch across through kindergarten through 12th grade and are truly central to understanding how science works and what we know about the world? In physical science, there are 4 different disciplinary concept core ideas. In life science, we have, again, 4 core ideas. In earth and space science, there's 3 core ideas. In engineering, technology, and the application of science, in that category, there's 2 core ideas. As you look at the core ideas, they're given some depth by identifying component ideas. So component ideas are, again, big ideas that are related to each of these core ideas, and really kind of give depth to these core ideas. Finally, as you think about disciplinary core ideas, we introduce the idea of learning progressions. So a progression is a coherent K-12 developmental sequence for each of these component ideas. So now as you think about the way that standards are structured and the way our science curriculum should be structured, is we'll have a small number of really big ideas that we start developing early in elementary school and continue to build on those ideas all the way through into high school. So it gives us a nice coherent sequence and structure to our curriculum. So the reason why it's important to have an understanding of those three dimensions, in the case of this video, just a very snapshot of those, is because what the standards do is they take those three dimensions and they integrate them into performance expectations. So when you read the standards document, what you'll be looking at are a series of performance expectations that have been grouped in certain ways. So a performance expectation, again, it integrates the science and engineering practices and integrates cross-cutting concept, and it integrates a component idea. It's also important to realize that these performance expectations are written as assessment guidelines. So it's not the curriculum. Instead, it's if a student understands this content or this concept, what should they be able to perform or what should they be able to do? So as you read these, you need to read them as guidelines for how we're going to assess our students, what we want our students to know and be able to do at the end of our course. As you look at a performance expectation, you'll see in parentheses often a couple of different statements. So many of the performance expectations have clarification statements. Those are ways to provide examples, or some way to clarify what is meant by a specific performance expectation. The other thing you'll see is statements of assessment boundaries. So many of the performance expectations will include an assessment boundary that says, you should be thinking about students being able to know and be able to do these types of things, but not going to this certain level. For example, it may be in an upper elementary class, students are thinking about things qualitatively, but not necessarily putting a mathematical equation to it. That'll be something that's developed later. The last thing I'd like to say about performance expectations as you go into to looking at the final draft or the final version of NGSS is the way the sheet looks, the way each page of the standards document looks. So it includes these performance expectations and clarifying and assessment statements at the top. And then you have what are called foundation boxes. So the foundation boxes show directly from the framework for K-12 science education, the text that explains what's happening in these performance expectations. So you have the practice that's identified in these different performance expectations, the core ideas, some more explanation of what's meant by these core ideas, and cross-cutting concepts for each of these performance expectations. So these foundation boxes really help to provide further explanation for what the performance expectation means and how that could translate into instruction for students. The final piece that's really exciting is called a connection box. So in the connection boxes, you'll see a few different things. First, you'll see how these standards pages are connected to other standards within the Next Generation Science Standards, but you'll also see how this specific set of performance expectations are connected to concepts from the Common Core State Standards for English Language Arts and the Common Core State Standards for Mathematics. So it's a way to assist you as you start to plan instruction in making those linkages between different sciences and different content areas.